To have a reaction, so if we want to have a chemical reaction, there are a couple of things that have to take place. Okay, first of all, there have to be collisions between molecules. So we can't just have some molecules over on one side and other molecules on another side and expect a reaction to take place. They actually have to collide. They have to come within a fairly close distance of one another in order to engage in an activity that will allow the valence electrons to rearrange. Another thing that has to happen is that there needs to be sufficient energy available. And usually that energy comes from the collision itself between the two molecules, although it also can come from the environment around those molecules. So in this case, there are a couple of different ways we can get it, but if we don't have that energy available, it turns out it's sometimes very difficult for these reactions to occur. The last thing that we need is during a collision, the relative orientation of the molecules must be correct. And what do I mean by that? Well, if the two molecules hit each other the wrong way, for example, if they hit each other at an end of the molecule that doesn't participate in the reaction, then they probably won't react. They'll probably just bounce off of each other and go find another collision to make. So this relative orientation is an important factor, but it's actually one of the most difficult ones for us to model in any sort of theoretical way. One almost needs to do simulations of molecules in order to test out this relative orientation thing for a lot of the most interesting and most complicated reactions. But if we start with these three premises, it gives us at least a place to start. So what we're going to be interested in is the movement of molecules, something we call molecular dynamics, which is written up here at the top. Molecular dynamics is the movement of molecules relative to one another, but in this case we're really interested in how they move and interact with one another that leads to reactions. Now, it's not the first time that we've dealt with molecular dynamics. If you'll recall, back at the very beginning of the course, we looked at a fairly simple version of something called the kinetic theory of gases. All right, and I'll just remind you of some of the aspects of that. What we did was we basically modeled gases as though they were little hard spheres that were just bouncing around elastically off of one another. And by using that, we were able to derive at least some fairly interesting relationships for gases that behaved in the way that the gases in our model behaved. Now, I should say that these really lead us to what you might call an ideal gas description of a molecular system. And in particular, what we have are particles that are dimensionless, that is to say they're point particles. We also have particles that bounce elastically off one another, so all collisions between particles are completely elastic, that is to say they conserve momentum. And finally, we have no intermolecular forces between the molecules in these models. So we don't have to worry about them condensing into liquids or solids, and we don't have to worry about other sorts of non-ideal behaviors, such as the ones that we've learned about at various points in this course. All right, we're going to, of course, move beyond to this particular aspect, but I wanted to remind you of some particular results that we got when we considered this simple kinetic theory of gases and we compared it to the ideal gas law. In particular, one of the most important relationships we found was that the average kinetic energy could be written as 3/2 kBT for a molecule. And the reason this is so noteworthy is it basically gives us a way to think about temperature. Temperature is related to the kinetic energy of the molecules in a system. We could expand this to a full system by multiplying through by Avogadro's number, and then it would just be 3/2 RT, but you get the basic idea. The whole point is that as we increase temperature, we increase kinetic energy, which means that molecules move faster. As we decrease temperature, we decrease kinetic energy and they move slower. Now, along the way to getting this, we also had other relationships. For example, I'll remind you that we came up with this one as one of our relationships between these quantities. But the whole point is that we can use these simple models for molecular dynamics to really probe systems and get some fundamental knowledge about how the different parts of these molecular systems are related to one another. Now, one of the things that in some sense arose from that kinetic theory of of molecules, of gases, is something that really was a result of Maxwell proposing something that was in line with some of the other properties that he had found for systems. And that was the proposal that led to this distribution of velocities for an ideal gas. Okay, this distribution, I'll remind you, had the following form, and it was this is a normalized function. That's why we have all these crazy constants here in the front. Okay, but the point was that this told us how to calculate, if you will, the probability that the molecule would have a certain velocity or be within a certain range of velocities if it was at temperature T. And you'll see that T is contained up here and also down here in this expression. All right, this Maxwell expression was later derived more formally by Boltzmann, and so this is called the Maxwell-Boltzmann velocity distribution. So I should probably write that down here, Maxwell-Boltzmann velocity distribution. And using this distribution, we can basically determine lots of different properties of a system of gas, particularly if it happens to be an ideal gas and has these various qualities associated with it. Now, one of the things we didn't talk about at that time, but I want to emphasize now, is that this came about because we could treat the gas as isotropic. That is to say, it's the same in the x, y, and z directions, which means that if I want to write down a function that sort of describes the propensity for a molecule to have a certain velocity, I could do this, and it wouldn't matter which dimension, x, y, or z, I'm talking about. It would be the same in all of these dimensions, and it would look something like this. Oops, kBt raised to the 3 halves e to the minus mv squared over 2kt. Okay, so it's really just this piece of the Maxwell-Boltzmann distribution with this normalization factor. And the reason we can do this is that these other pieces, and I should probably point them out here, this piece and this piece and this piece are really all just part of the volume element for spherical polar coordinates. So the part that really has the meat in it are these other pieces. This piece, which is a normalization constant, and this piece, which tells us how the function varies with the velocity of the molecule. But the fact that all of these things could be equal means that we have, if I call this fx, fx is going to be the same function as fy, which is going to be the same function as fz. They're all going to be the same, and that means that we can draw some interesting conclusions about this. Now, one last thing I want to do is to draw what this function looks like, because this is really telling us how the velocities are distributed in a given dimension. So if, let's say I'm talking about the x dimension, so I might draw a picture that looks like this, and I'm talking about f of x as a function of its velocity. So maybe this is really the velocity of x along here. All right, what we find is that this function is basically a normalized Gaussian distribution, and a Gaussian distribution is the one that looks like a bell curve. All right, so something like this. And this bell curve would correspond to a particular value of temperature. And if I were to go, for example, to a higher temperature, so let's go, we'll make a higher temperature be red, that higher temperature would look flatter and broader than the first. So this is at a higher temperature. And it's important to be able to make these distinctions here, because as we go to a higher temperature, it means we're sampling higher velocities. These velocities are both positive and negative in this case. I've defined 0 here in the middle, because it doesn't matter whether the molecule is traveling in the forward direction or the reverse direction. It's still part of that overall distribution. But this represents a continuous probability distribution of velocities, and we can use this Maxwell-Boltzmann continuous distribution to determine various properties that are related to velocity in a system. And we'll talk a little bit about that in the next video.